So yesterday we are discussing that how atoms become magnetic. So most of the atoms in principle are magnetic because they have electrons, and as electrons also have magnetic moment. So therefore the atom also should be magnetic. And the magnetic moment is basically is a vector sum of its spin contribution or due to orbital contribution and also due to the nucleus. But the nuclear part is negligible because it's very small. The magnetic moment due to the nucleus is very small compared to the electrons. So that gave to two different possibilities. So one is like if all the electronic energy levels are completely full, so then you will not have any magnetic moment. So that gives rise to diamagnetism. And then the second possibility is, so there is a partial cancellation. So you will have a finite magnetic moment, and that gives rise to paramagnetism. So we discussed also this diamagnetic part. So a diamagnet is basically has zero magnetic moment when there is no field, but when you apply a magnetic field, so it will uh, produce a magnetic moment so that it will oppose the magnetic field which in the first place induced it. So it is something like Lenz's law, what you have known. And although the origin is actually a quantum mechanical origin, so maybe when you do a science related course to quantum mechanics, you will understand how diamagnetism actually comes from uh, due to these electrons. But in a classical, uh, so we will only stick to the classical description in this course. So we will not really go into quantum mechanical descriptions unless it is really required. But magnetism, always remember, magnetism is actually a real quantum mechanical phenomenon. Okay, so which materials are diamagnetic? So mostly, I mean, all materials which have all the atoms with fully filled electronic cells, so they are diamagnetic. So if you take example any inert gases, so they are diamagnets. Now, many molecules with ionic and covalent bond. So actually, they also satisfy this condition that the electronic cell is full because the electron will be shared. So sodium chloride, for example, is an ionic solid. So it is also diamagnetic. Then water molecule is also diamagnetic. Nitrogen, that is also diamagnetic. So carbon, so in graphite form, that is also diamagnetic. But again, you see here the diamagnetic property is a bit anisotropic. You see, so this parallel means so graphite is like a layered structure. Okay, so it's like a hexagonal layered structure. So again, this is a hexagon which has two different, so hexagonal plane and one is perpendicular plane. So the diamagnetic susceptibility is actually anisotropic in this material. And then many organic molecules, so benzene, toluene, those that these are used in organic chemistry, so they are also diamagnetic actually. So unless you have, let's say, like if you remember the periodic table, okay, this magnetic periodic table. So unless you have one of the magnetic atoms, normally you will not get any paramagnetic or ferromagnetism. So most of them will be uh, diamagnetic. But one exception is oxygen molecule that is paramagnetic. Okay. So when you compare like the diamagnetic properties, so in terms of electron pairing, so you have no unpaired electron for an atom, and they oppose the magnetic field which is responsible to induce the magnetic moment. So they are opposite to the magnetic field or the magnetic induction. So they are basically will be repelled by a magnet. Okay, and how the field line should look like. So typically, so if you have a material which is non-magnetic, so magnetic field lines normally should go just straight, but here you see a little bit bending of the field lines due to the diamagnetic properties of the material. So we always talk about this M and H, so in ferromagnets, and also susceptibility. So when we want to compare, so diamagnetic or paramagnetic or ferromagnetic materials, so we have to compare how the M and H or the susceptibility versus temperature. So these are the typical measurements, experimental measurements normally done to understand or know experimentally whether this material is diamagnetic or paramagnetic or ferromagnetic. So if you measure a substance, an unknown substance, and measure the magnetization versus field, so for a diamagnetic material, you will have a negative slope, right? So it is because chi is always less than zero. Why? Because when it induces the magnetic moment, that magnetic moment opposes the field, applied field. So therefore, it is opposite to that, and chi will be always negative. So if you get such a negative slope, so then you know it is a diamagnetic material. So there is also another way to look at it. So if you measure the susceptibility versus temperature, so then also you can understand or differentiate between different magnetic materials. So for diamagnetic materials, this susceptibility is negative. So we are in the negative axis, and it is constant. So it is not actually affected by a thermal energy or temperature. Um, and one thing, look, so when you increase the magnetic field, the M, the magnetization is increasing. So higher the magnetic field, so higher will be the magnetization. And therefore, temperature does not really play any role in diamagnetic materials. Okay, so normally a diamagnetic material will have a constant susceptibility as you change the temperature. But this susceptibility dependence on temperature is different for a paramagnet. Okay, so this is another very interesting material. These are called superconductors. So superconductors are materials which actually have no resistivity or zero resistance below a certain temperature. Normally, it is below like much lower than the room temperature. So even very close to 0 Kelvin. So typically, some metals like mercury, the resistance becomes zero at 4.2 Kelvin. So room temperature is 300 Kelvin. Okay, compared to that, so if you go to 4.2 Kelvin, so then that mercury becomes superconductor. That means it has zero resistance, uh, and that is like one of the interesting material in physics. Of course, it has a lot of potentials in future, but unless you get a room temperature superconductor, it is, I mean, doesn't make sense for any real application. And that is why a lot of people are working on understanding the origin of superconductivity. So once you understand, so probably you can better design materials which would be superconductor at room temperature. So why you need superconductor? I mean, we will discuss maybe after we finish. So we have one last chapter dedicated to superconductor. So we will discuss in that. And for superconductor, they are known as really at least one some kind of superconducting materials. They are known as perfect diamagnet. So perfect diamagnet means susceptibility will be oh sorry, this will be -1. Okay, so it's not 1, so it should be -1. Okay, so I'll just correct it, and when I uh, share with you, I will do that. Okay, so this would be -1 because it is a diamagnet. Okay, so the second possibility is it should be when the cancellation of the magnetic or the atomic moments or the electronic or the electron's magnetic moment does not cancel. So there is a partial magnetic moment, and they are called paramagnets. And they typically follow this Curie law. But if they are actually a ferromagnet, so they will follow this Curie-Weiss law. So these laws were actually known as empirical laws. So for example, Curie. So so the husband and wife, Pierre Curie and Marie Curie. So they worked on radioactivity. So that Pierre Curie, so he worked on this magnetic materials, and he measured the susceptibility as a function of temperature. Okay, and then he came up with this empirical formula, uh, which says that okay, this is a paramagnet or a ferromagnet. Okay, but there was no theory for paramagnet for a long time actually. Uh, so to understand the theory, so why we are really interested in diamagnets and paramagnets? So maybe some of you might be asking this question. Uh, you know, really paramagnet and diamagnet do not have any application. So right now, maybe some diamagnetic properties are being exploited, but not really as widespread as the use of ferromagnets. So why do we need to understand diamagnets and paramagnets? Uh, One of the reason is, I mean, they are easy, so to model, theoretically understand them, and then this understanding will actually lead to a better understanding of ferromagnetic properties and the origin of ferromagnetism in materials. So that's why in any classic magnetic books or any course on magnetism always starts with diamagnetism and paramagnetism. So once you understand these simple things, so then you can build upon it and then understand ferromagnets better. Okay, so that's why we are going through this in a step-by-step process. So, so what is a paramagnet? Then, you have partially filled orbitals, and that gives rise to a finite magnetic moment. Uh, so the assumption, so when the theory was developed, so again, we are here only talking about a classical explanation of paramagnetism. So in magnetism, we always have like two different explanations. So until any theory which was developed, let's say until 1915, so they are all mostly classical theories. They were able to explain this paramagnetism and diamagnetism really successfully, but they were not really successful in explaining ferromagnetism. And therefore, one has to go from a classical explanation to a quantum mechanical explanation or the understanding of magnetism. But if you compare a classical and quantum mechanical description of paramagnetism or diamagnetism, there is not much difference. Okay, so maybe a minor, like improve the order of the understanding a little bit, but not much. So qualitatively, you can even understand, or even sometimes quantitatively, also many paramagnetic behavior could be described using classical mechanics. So, of course, when we start with the understanding, so you start with some assumptions. It is not like you can just go and do it that easily. So we have to assume, and based on that assumption, we develop this theory. Uh, so one assumption is atoms or molecules have same magnetic moment. So this does not mean if atoms have different magnetic moments, they cannot be paramagnetic, but that is not true. But from a theoretical understanding, it was easy to develop and assume that, okay, atoms and molecules, so we take same kind of magnetic moments. And the second thing is they are non-interacting. So there is no interaction between the any two moments. So now this is something like a distribution of magnetic moments, which is in absent of magnetic field, and they are all random, right? So what happens when you apply a magnetic field? So all of them will try to align along the magnetic field. So that means all will be pointing in along the field direction. So in diamagnetism, it was opposite to the field, but in paramagnets, it is along the field lines. So that is the difference. So that means it will have a very high magnetic moment. But in reality, paramagnets do not have very high magnetic moments. And one of the reason is, so we actually neglect or forgot about the thermal energy or the temperature. So normally temperature in any system so is there to randomize the things. So it will increase fluctuations and randomness into the system. So this is also true for uh, this magnetic moments as well. So magnetic field is trying to align it. When you apply the magnetic field, it is trying to align it along this field direction, but there is a thermal energy. So thermal energy is typically expressed in kb into T. So T is the temperature, kb is a Boltzmann constant. So that kbt thermal energy is always there to disturb this equilibrium, okay, or change or randomize the spin. And that's why, so there is always a competition between your applied magnetic field and the temperature, and depending on the ratio, so you will have magnetization or not. But always you will have some finite magnetic moment which will be aligning along the magnetic field, and that will give rise to some finite magnetic moment, positive magnetic moment in uh, paramagnet. Okay, so when you compare so this is the picture from diamagnet. So if you compare the same thing in paramagnet, so you have electron pairing which is partially filled. So this is one of the cell is not completely full, and then of course when you apply a field, the magnetic moments are aligned along the field, so they have a positive susceptibility. So this means they have a negative susceptibility, and paramagnets have a positive susceptibility, and they will be normally attracted to a magnet. So weakly attracted, so not really also strongly attracted, but they will be attracted towards a paramagnet. And then the field lines like somehow bend towards the material, so they will try to concentrate the field lines passing through them. Okay, so we will do a small, or I have already done a little bit of. Now we go into a mathematics. So far, actually, you have seen like I have not really used many equations. Many we haven't done any mathematics, and that is what I want to do. Is that mostly we will not do a lot of mathematics in this course. You have done already a lot of that, and you are really good in mathematics. That I know. Uh, but here, to understand the paramagnetism, we will do a little bit of mathematics. So what is done here is actually, so we assume that we have a field, let's say along the z-axis. So this is our z-axis. So this is the field direction, and then we assume that our magnetic moment. So these are our magnetic moments of the vectors. So these are basically vectors, and these vectors have uh, so you can consider them that they are somehow arranged in such a way that in a sphere, and they are passing through the origin or the center of the sphere, and they are projected onto the surface of a sphere. So since they are all the same magnitude, so the radius we can distribute on a surface when they are distributed. So they will form a sphere, or this vector will be up to the surface of the sphere, And this is like, you can say this is your magnetic moment mu. And if you say, okay, we can put it in a sphere with unit radius, so where the r will be equal to 1, and then we assume that, so in the beginning, let's say when there is no field, so these moments will be all random. Okay, so they will be pointing in any direction. But so if you look at any surface on the sphere, so you will find the same number of magnetic moments. And that's why when you take the average over the entire surface of the sphere, you will have a zero magnetic moment. But now if you apply a magnetic field, so the magnetic moment will try to align along the field. So now, I mean, they are not exactly parallel to it, but they will try to probably be probably they will be at certain angle to the magnetic field. So in the absence of field, this theta angle will be anything, right? But now, so most likely they will prefer to align along the field, and let's say they make an angle theta, and what we are doing is actually we want to calculate what is the fraction of, so let's say we have, maybe I will, okay, yeah, this is just the thing which I told already. So the magnetic moments are represented by vectors passing through the center of the unit sphere, and we want to calculate the number of or the fraction of moments which are aligned between theta and theta plus d theta. So I'll just go to the other slide. Okay. So we say, let's say we have n is total number of moments. So this is to be total number of moments per unit volume. Okay, so we assume that. So that is n. So we want to calculate dn, which is the fraction which are aligned at an angle theta and theta plus d theta. So when the field is zero, so this fraction will be proportional to this dA, which is basically this annular ring, which the moments will be aligned along that surface. Okay, so that is the area of that annular ring. So which is for a unit sphere will be 2 pi sine theta into d theta. Okay. And then what is the potential energy of those magnetic moments? So that is minus mu h cosine theta. So what you can assume that, so now the projection of the magnetic moments, so or the magnetic moment will have a magnetic moment, the value is magnitude is mu cosine theta multiplied by h. So that is your, you have an effective moment uh, projected on your field direction. Okay, so and let's say we are at a temperature T, and you want to find out, so what is the probability that an atom having energy E is given by this Boltzmann factor. So this is exponential minus EP by kBT. So this is like a Boltzmann, kB is your Boltzmann constant, and this is the probability that that atom will have energy EP. So energy EP means this potential energy mu h cosine theta. So that means what is the probability that an atom uh, has a moment mu and at angle theta. So that is exponential minus mu h cosine theta by kBt. So that is the probability. And to know the number, so you basically have to multiply this area into your probability function, and here, so this dn, the fraction which are aligned along the angle theta or between theta and d theta is given by this, so k is basically some constant, uh, and dA exponential e minus ep by kBt. So if you substitute the value of dA and energy, so you'll get this expression, and then we can calculate, so the total number will be you just integrate it from 0 to n dn. So that is your total number of moments per unit volume. And then we can solve it, this integral, uh, and you substitute that. So I'll send it and you can do it on your paper so you understand it better how the mathematics is done. So I'll just skip it quickly. And finally, what you can get is the magnetization. So the magnetization is basically you have your magnetic moments mu, and you just have to sum all the magnetic moment, so you will get a magnetization, right? So that is your net or the magnetization on the ring. Now if you want to take the calculate the total magnetization, again you have to integrate from 0 to n with all the magnetic moments and the fraction within that theta and d theta. If you do that, so you will get, this is your total magnetization, uh, and so we did some simplification here. If you do that, you get, so I am not going into the detail of the mathematical steps here. So you can do that by yourself. And finally, if you do the simplified thing, so what you obtain is this equation. This m by ms will be equal to cut hyperbolic. This is a hyperbolic function of this form. Okay, so this is so you need not solve the whole equation or the integral. So this is like what you, the final result you will get. Okay, so this has a special name. This is this function L. It's called a Langevin function, which is given by this. So when this got hyperbolic a minus 1 by a, and if a is smaller than or equal to 1, so it is of this form. Okay, so you can expand it in this way. So basically your magnetization m by m0 or ms. So what is ms? So ms is basically your maximum magnetization, so maximum moment. When all the magnetic moments are aligned, so you'll have the maximum moment, saturation moment, let's say. So it will be ms, which is n into mu. Okay, so here we are basically talking about what is the magnetization fraction with respect to the saturation magnetization. Yeah, so this is called a Langevin function. And so for small a, so when you have very small is a is much smaller than 1. So remember, a is basically your mu h by kbt. Okay, so it is smaller than 1. So in that case, you can write the equation. So you can neglect all of the higher order terms here. So we have only a by 3 term. So other terms you neglect. And we have something like this. And now if you want to calculate susceptibility from it, so susceptibility is m by h, so which will be n mu square by 3 kbt. So this is called as volume susceptibility. So if you divide by rho, so you will get a mass susceptibility. So one thing what you clearly already see here, this susceptibility is proportional to 1 by t. Okay. Let me go back to this slide. Yeah, so the susceptibility, when you plot that function, so this Langevin function, when you plot, so we have m by m0, which is our Langevin function, which is proportional to 1 by t. And when you plot that as a function of a, which is mu h by kt or kbt, so for small a, so it is almost like a straight line. Okay, but if you go to larger a, then it is getting to into a like a saturation kind of form. Okay, so it is getting saturated, starts from zero, of course, and then getting saturated. So this is again the same function which is plotted in both the quadrant. So in the first quadrant, it will be in this way, and in the third quadrant, it will look like this. So now you look at the difference. Remember the difference between a diamagnet and a paramagnet. So in a diamagnet case, so the line was going something like m. So if you plot that m versus this function, so it will be like a negative slope you will get. Okay, but in a paramagnetic case, you are getting something different. Okay, so this is how you can actually differentiate between a paramagnet and a ferromagnet. So remember, for a paramagnet, when field is zero, m is zero, magnetization, no magnetization. Only you will get a magnetization when you apply a magnetic field. The slope is basically your susceptibility. So now if you plot the chi versus T temperature, so uh, so you can see the slides now, or is it? Slides are visible? Ah, okay. Uh, yeah. So now if you look at the susceptibility versus temperature dependence, so this is basically your, for a paramagnet, this is how it looks like. Okay. So 1 by T behavior. So chi, we saw that chi is proportional to 1 by T. So this is 1 by T behavior. And for a diamagnet, it is negative and very close to zero. So very small, and it is almost close to negative, but close to zero and constant. We saw that before. And this we will do that in the next class. So next class, so today afternoon we will have no class. Okay, so we will meet again on Monday morning. Okay, so in that next class, so we will consider this plot in detail, try to understand it. Okay, any question? Yes. Uh-huh. Mhm. A is anyway. I will share it. So A is basically your mu h by kt. So that is, we substituted A. So to simplify, uh, yes, 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 exactly, exactly, yes. So this is yeah. So this is your G-man energy, sometimes called a G-man energy also. This, or the magnetic energy, and this is your thermal energy. Yeah. Yes. This one. Huh. Hmm. Yeah. Yes. 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 That is the only difference. Yes. So here it is only in the first quadrant, in the positive part. So here you see both positive and the negative part.